Hi everybody, the purpose of this video is to go over section 1 of chapter 8, and we are going to use confidence intervals to estimate population means. Specifically, we're going to talk about the idea of a point estimator. In other words, using a collection of values to estimate a certain parameter, namely the population mean. We're going to see how our point estimator can be used to construct a confidence interval if we can determine what the margin of error happens to be. And once we figured all this stuff out, guess what we're going to do? You guessed it, we're going to construct confidence intervals. Okay, so we want to estimate the value of a population parameter. Basically, we want to estimate the value of its population mean. Population is way too big for us to basically compute all the values in the population to consider it. So we need to take a sample and use that sample to estimate the mean. Of course, that means we are going to create this thing called an estimator, which really by itself is also a random variable that has a mean and a standard deviation. And this estimator, which once again is a random variable, actually has to have two properties to be considered a good estimator. The first one is it has to be unbiased. What does that mean? It means it should not consistently overestimate or underestimate the population parameter, the population mean. Okay? On the average, it should, on the average, the estimator should be equal to the population mean, on the average. The other criteria is that it must be efficient. Okay, well, what the heck does that mean? That means that as the sample size increases, the number of samples you take increases, then the variance or the standard deviation of your estimator should go down to 0. In other words, if you increase the sample size enough, it should asymptotically approach the actual population parameter, the population mean. Okay? And as you might guess, a good estimate, a good point estimate for the population mean is the sample mean. So let's talk about how we could actually compute, in this example, a point estimate for a mean of a particular population. So here we want to find the best point estimate for the population of mean test scores on a standardized biology exam. We only have 5 samples. What is and these are only 5 samples. What is our best point estimate for the population mean? Well, that would be the sample mean. How would we compute the sample mean? Well, the sample mean is computed by adding up the samples, and dividing by the number of samples. This will give us 376 divided by 5, which happens to be 75.2. So my sample mean is equal to 75.2. Boom, we're done. Now, what does that tell you about the population mean? Doesn't really tell you much. We know that we have a sample mean of 75.2. But there is actually no measure of how that actually relates to the population mean. Is the population mean over here? Is it over there? We would like to think it's close by, but it's not really sure. But we're not really sure. So it might be good if we actually came up with an interval estimate. In other words, an interval estimate that starts at this value and that starts with this value. And then we can say that the population mean is somewhere within this interval with a particular level of confidence. In other words, we can say that the population mean is that I am 90% sure, or that for a probability of 0.9, the population mean is somewhere within that interval, or with a probability of 85%, the population mean is within some side of that interval. So we want to have an interval estimate, and we want to have a level of confidence associated with that interval estimate. Okay, and we're going to call that C. And sometimes we'll express it as a decimal, sometimes we'll express it as a percentage. Okay, so we are creating a confidence interval. And the bounds of the confidence interval are going to be determined by an error which we actually need to compute. Okay, so this distance right here is an error, so this would be x bar minus e. And this distance over here is also basically associated with our margin of error, and so this point will be x bar plus e. And of course, this error is going to be some function of your confidence interval, or some function of your level of confidence. Okay? So basically our confidence interval works by, we come up with our point estimate, we come up with E, all right, and then we use that to compute our confidence interval, and we use that to compute our confidence interval. Here, this once again, this will be x bar minus E, x bar plus E. For that point right there. And this pretty much just says the exact same thing again. Level of our confidence interval, a level of confidence determines our margin of error, and of course our data determines our sample mean, and from that we can compute our confidence interval. Now, what does it mean if you actually have a 90% confidence interval? Well, that basically, now if you think about this, when you are computing a confidence interval, you are going to take a sample of data. That data is going to produce for you a sample mean. Okay, it turns out that the error will be determined by this particular value, which will give you your confidence interval. So basically, every single interval is going to have the exact same length, but the midpoint is going to be determined by the sample mean, which will be determined by the sample. So if you take one sample, you're going to get a certain sample mean, which gives you this confidence interval. If you take another set of samples, I'm going to call that N2. You will, of the same size, you'll get a different sample mean, which will shift it around, and so forth, and so on and so forth. Now, your population parameter never changes. This is what it is. It's this particular number here. Now, if your confidence interval is 90%, that means that if you've done this 10 times, took 10 different samples, produced 10 different sample means, constructed 10 different intervals, 9 out of those 10 will contain the population mean. 1 out of those 10 won't, which basically means there's a probability of 0.1 that your confidence interval will not contain the population mean. If it was an 80% confidence interval, then that means that 2 out of 10 would not contain the population mean inside their interval, and that's pretty much what what it means. Of course, we will always, the consequence of that is that the probability that the sample mean is inside the confidence interval will inside the confidence interval will always be equal to your level of confidence, and the probability that it's not will always be equal to 1 minus your level of confidence, which is typically what we call alpha. Okay, so how do we construct a confidence interval? Well, for this particular problem, we have a college student researching study habits, there we go, collects data from a random sample of 250 college students on her campus and calculates that their sample mean is 15.7. If the margin of error using a 95% level of confidence is 0.6, construct a 95% confidence interval for her data. Now, to construct our confidence interval, we need two things. We need the sample mean, we need the margin of error. Nothing else. If we have these two things, nothing else matters. Okay, cool. There's our sample mean, 15.7. Here's our margin of error, 0.6. Okay, if that's the case, then our confidence interval is going to start at x bar minus e, which will be 15.7 minus 0.6, which will give us 15.1. And it's going to extend all the way up to x bar plus e, which is 15.7 plus 0.6, which will be 16.3. Okay, so if you know what E is, it's a snap. Well, what if you don't know what E is? Well, then that means we need to figure it out. Now, and for most of our problems, at least in this particular section, we can take advantage of the central limit theorem, which was a theorem that we skipped over in Chapter 8. The central theorem pretty much says, central limit theorem says this. If you have a large enough samples, then your sample mean, remember sample mean is a random variable, it's a point estimate, will have a normal distribution. But there are a couple of criteria. First thing is the sampling must be random. We have to know what the population standard deviation is, which is actually kind of silly because if we know what sigma is, then we also already know what the mean is. And then, because you need this to compute sigma, and then the sample size must exceed 30. If we have these, if these criteria are met, then you can assume that the population mean has a normal deviation. What does that do for you? Well, it pretty much means that your population mean is going to look like this. And if you are looking for a confidence interval for a certain level, or a level of confidence interval with a level of confidence of say C, then you are saying that the population mean is going to be somewhere in the middle of that normal distribution. Okay, which means that we need to figure out what these values are right here. These are what we call the critical values. Okay, now remember, if this is C, the area in the middle, then the area in the tails is alpha. So this plus this is alpha. Okay, and then the area in exactly one of the tails right here is alpha over 2. So we can use the lessons that we learned in Chapter 6 to find out what the critical value is for a given area to the left of that particular point. And remember, if C is 0.95, alpha is going to be 0.05 in this case, and alpha over 2 is going to be 0.025. So we want to find out the area. We want to find out the value Z. What value Z is going to have the area. We want to find the value Z where the area to the left of Z is equal to 0.025. That happens to be negative 1.96. Of course, we don't care about the negative. We only care about the positive. So this is our critical value. And this is what we're going to use to compute our error. Now, this right here is the critical, as the table shows the critical values for other levels of confidence that we'll be interested in. For example, if you want an 80% level of confidence, your critical value is going to be 1.28. If you want a 95% level of confidence, there it is, 1.96. If you want a 99% level of confidence, then your critical value has to be 2.575. So this is the table that you can use to find out your critical factor for different levels of confidence. Great. How can we use this? This is how we can use this. If you want to figure out what your error is margin of error is always going to be equal to your critical value for the given level of confidence, okay, times your standard deviation divided by the square root of your sample size. And once you have that, then we can figure everything else out. And that's actually, now before we do that, let's talk about the rounding rule for endpoints. Okay, now, in our particular case, we're not going to be given any data, but we're going to be working with statistics. In other words, I'm going to tell you what the sample mean is. Okay, so since we're giving statistics, we need to round to the same number of decimals that is given in the standard deviation or variance. Now remember, the variance is nothing more than the standard deviation squared. So if you are given the variance, you need to take the square root to get the standard deviation. So how do we construct a confidence interval? We find the sample mean. This will be given to us. We find our critical value using this table right here. We compute our margin of error using this equation right here. Then our confidence interval is going to be your sample mean minus your margin of error. This will be your lower limit. And your upper limit will be the sample mean plus the margin of error. And in our next video, I will show you how you can actually do this by working out an example. And until then, this is Bob Boyle signing off.